All right, so we're going to begin our discussion of thermodynamics, statistical thermodynamics rather, by looking at a quick math review. So let's say that we have a data set of discrete or individual and whole values, where we have x is equal to 1, 2, 1, 1, 3 that we've taken over the course of our measurements. And then we also have a set of y values, where every time that we have a value of x, we just square it. So for x is 1, y would be 1. For x is 2, y is 4, and so on. It's possible for us to calculate the mean or the average values of x. So again, we're going to look at our set of x values. We're going to add up, doing our average that we learned about in algebra, where we take each of our individual values of x, we add them all up, and then we divide by the number of values that we have. In this case, we had 5 x values, so we would be dividing by 5. Now, we could also write the average a little bit differently, where we know that we've got 1 that was measured 3 times, 2 was measured once, and 3 was measured once out of the 5 times that we ran it. So again, for the value of 1, we measured that 3 out of the 5 times. We measured 2, 1 out of the 5 times, and we measured 3, 1 out of the 5 times. So if I were to add those up, those are mathematically equivalent. We can write this generally as the mean of x is equal to the sum on j, for j goes from 1 to 3 in this case, our x values times our probabilities divided by the sum of our probabilities, and that's going to be our normalization. Again, if we add them all up and it has been normalized to 1, then our sum of the probabilities would be equal to 1. So again, in this last equation, P sub j is the probability of measuring the jth event. If we are dealing with discrete particles, then the ensemble average of any given property, which would be a function of x, is going to be the ensemble average of our function of f of x is equal to the sum on j, starting at 1, of our function of x times our probability of x. Okay? Thus, the normalized mean of any function would be given by f bar of u, which is going to be the integral of f of u, p of u, integrated over u, divided by the integral over our probabilities. All right? So essentially what this is saying is, if I wanted to measure the y of x, the mean, or the ensemble average of the property y of x, then I would plug in my y of x values and the probabilities of measuring the x. Now, since we keep talking a lot about probability, let's write down several possible distributions. The first of which is our Gaussian distribution. Here, the probability of x is given by 1 over the square root of 2 pi sigma squared times the exponential of the quantity of the quantity of the quantity. So it's basically the exponential of the difference between our measured value and the mean, product squared, divided by 2 divided by sigma squared, where x can be any value from negative infinity to positive infinity, and where sigma squared is our variance, which is essentially the spread of our distribution. All right? Now, for our next distribution, we're going to need Stirling's approximation.